Today we're going to be doing section 15.1, and it's double integrals over rectangles. So we know how to do single integrals, but single integrals is actually Calc 2. What does a double integral look like, and what does it calculate, for want of a better word? Right, I want you to imagine that this curved surface here represents the function z equals f of xy. So it might be z equals x squared minus y cubed, right? So we've got this function, which is essentially going to be written here. When you do a double integral, I guess the name implies that you're going to integrate twice. You're going to integrate with respect to the variable y and x. So all double integrals integrate using the two typical, x and y variables that represent the floor of this shape. Now, the notation, you can have dy and dx or switch it dx, dy, that's totally okay. But if you decide that dy goes here, this limit of integration 1 and 4 means that the y's are going from 1 to 4, and this limit of integration 1 to 2 is attached to the x. Do you see the x's go there and the y's are a little bit nearer? So if you put these limits of integration together, what you end up with is a rectangle. That rectangle there. It's going to be on the floor, the xy plane. And then what you would do if you calculated this double integral is you can imagine this rectangle projecting upwards until it hit the surface, and it would hit it at various points. And this bit at the top is not a badly drawn rectangle. Because Z is curved, can you imagine it's probably going to be more like a curved rectangle, right? At least 2 or more, or all 4 sides are curved. Well, this double integral represents the volume of this shape. So if you imagine this was a solid shape, I don't know, piece of cheese that you cut very weirdly, that was curved on the top. One of the ways to interpret the double integral is this area here. Now, if the shape is above the xy plane, this volume, which is represented by that double integral, will be positive. If this shape is actually below the x-axis and you do the double integral, it will be negative. And so it's not the kind of volume that you're used to in real life, but it is very similar to area above a curve and area below a curve. So can you imagine that a double integral, this guy here, will be a number, and that number could be 5 because most of the shape is above the xy plane. It could be -10 because most of the shape is below the xy plane, and it could even be equal to 0. Can you imagine a shape where, this curve actually passes through the xy plane, so some of the shape is above and an equal amount of volume is below. So when you do these calculations, do not freak out if your final answer is 42, -10, or 0. As long as you've done the math correct, you're good to go. So far, so good? Now, here is a full question with all the details. This bit here is essentially the surface f of xy, right? And we're being asked to do a double integral from 0 to 3 and from 1 to 2. And you can tell by matching the d's to the first one and the x's to the second one, the dy's, I should say, to the first one and the dx's to the second one, that you're integrating from y equals 0 to 3 and that you're going to do dy, and then you're integrating from x equals 1 to 2. I use this notation rather than that one. I mean, it's the same thing. If you look at it, it's just extra numbers. The reason why I prefer this notation is that later on, you are going to be integrating not over a rectangle on the floor, but maybe half a circle, maybe a triangle, maybe some weird curve. And it's very helpful to know who the x and y's are in terms of that, because the next section you'll do next week, for instance, you might be doing y equals 0 to y equals the square root of x, x equals 1 to x equals 2. So it's kind of helpful to do that. So let me rewrite this guy down again and show you how you would actually find the double integral. So right now I'm just rewriting the question. The best way to do or to think about this question, in my opinion, is to break it into two distinct bits. The guy I've just put those square brackets around is the first thing you do. So you do these guys from the inside out. So forget about the two guys at the end, except to realize that there's going to be an x equals 1 to x equals 2 here, and at the end there's going to be a dx. So let's see what we have to deal with here. You're being asked to integrate this expression with respect to y. So it's very similar to differentiation with respect to x, or partial differentiation with respect to y. The rules are the same, which is y is a variable and any other letter of the alphabet is treated like a constant. So let's see what happens. If you take 6x squared y and you integrate it with respect to y, that's basically a number. So you're going to do a power rule, which means you're going to add 1 to the power and then divide by the power. So if you divide this by 2, you now get 3x squared. Are you happy about that piece when you integrate it? Is add 1 to the power and then divide by the new power. Now, be careful about this one. I know it only has x's in, right? Negative 4x. And you're going to integrate it with respect to y. But if that was the number 42, wouldn't this answer be 42y? And if it was negative 4, wouldn't it be negative 4y? So you integrate a constant. It's not like differentiating a constant, you get 0. When you integrate a constant, don't you get the same constant with a y tagged onto the end? So this guy is now 4xy. Are we cool with that? I'm doing the usual rules of integration, right? I'm just realizing that y is a variable and I'm treating everybody else as a constant. Okay. So what I'm going to do now is evaluate it at y equals 0 and y equals 3, right? That's what you would normally do. So it's now going to be the integral from x equals 1 to x equals 2. But if you plug in 3 here, you get 3 lots of x squared times 3 squared. Take away 4 lots of x times 3. Take away, if you plug in 0 here, 4x squared times 0 squared gets me 0, and 4x times 0 gets me 0. And we get that guy. Now what do we get? We get x equals 1 to x equals 2. 9 threes is 27 x squared. And 4 times x times 3, that gives me negative 12y. Take away a whole load of nothing, so we don't worry about them. And that's an x, by the way. Dx. So once you've done the variable y, right, once you've done the dy part, you're now going to be left with a second integral. That's why they're double integrals. But if you notice that the second integral only contains x's, and this second integral is really just a calc 2 integral, right? There's nothing special about it. It's exactly the same thing. So add 1 to the power and divide by the new power. Add 1 to the power and divide by the new power. Evaluate it at x equals 1 to x equals 2. And then plug in your numbers. So what's that going to get me? 9 lots of 2 cubed. Take away 6 lots of 2 squared. Take away 9 lots of 1 cubed, which is just 1. Take away 6 lots of 1 squared, which is also just 1. 2, 4, 8, 72. 2, 4, take away 24. 9 take away 6 leaves me with 3. 72 take away 24, take away another 3. What's that going to get me? 72 take away 27. Okay.
45.
Thank you. Too late in the day for my brain to do that right. 45. So the double integral, this one here, the answer is equal to 45. Okay. How does that process seem? It's an extension of doing a normal single integral, but now we're going to do it over two variables rather than just a single. Any opinions? Does it seem like it has a structure to it? Yeah, okay. Now, minor thing, but it might be interesting to tell you. If someone gives you a double integral and it looks like this means do the y's first, right, and do the x's second. And I'm doing that bit where I'm not putting x's in. It's exactly the same because it's a rectangle, right? Because both limits are numbers. It's exactly the same as doing this guy. Do you see that? And so that's an interesting property, right? You can do the y's first and then do the x's second, which is this one. Or you can do the integration with x's first and y's second. Do you notice that if you move the order, you have to switch, right? These guys, right? And they are totally identical. Why might that be useful? Can you imagine that there's an integral out there where if you do it with the x's first, it might be a little bit easier than trying to do it with the y's first, right? So you can imagine an expression where maybe there's a lot of y's and very little x's going on. Then integrating with respect to x in that situation might be helpful. But I guess it's up to you whether you even bother to look to see whether changing the order might make your life simpler. So let's try another one. This one is similar to question 3. Suppose I am being asked to do this one from x equals 1 to 6 and from y equals 0 to 1. And I'm being asked to find x plus e to the negative y. Dx first, followed by dy. Right? So first thing, oops, did my white screen disappear?
Nope.
No, why can't I see it?
Now it did. Took a second to catch up.
Right, okay. Weird. Okay, so this is the double integral over the rectangle. We are going to get that guy first. So y equals 0 to y equals 1. There'll be a dy over here. If you integrate with respect to x, you use the power rule. What will I get if I integrate e to the negative y with respect to x?
X e to the y.
Yeah. And now I will evaluate that at x equals 1 and x equals 6. So it's going to be from y equals 0 to 1. If you plug in 6, you get 1/2 times 6 squared plus 6 lots of e to the negative y. Take away, if you plug in 1, well, 1/2 times 1 squared is just 1/2, and plug in 1 here, you get that dy. Now you have the integral from 0 to 1, and that guy is 18. 18 take away 1/2 is 17.5, so that's 35 halves. You get 6 of this guy, take away 1 of that guy, so you're left with 5 of this fella. dy. Hopefully I count right. Now we can integrate the number or fraction. That guy gets you y. Be careful on this fella. What do you get if you integrate 5e to the negative y? You do get 5e to the negative y. Do you get anything else? 5e to the negative y.
You would get a -1 attached to that.
Yeah. Now, it could be worse. That's bad enough. If it was negative 4y, right? So e to the negative 4y, you would get 5e to the negative 4y. But that 4, right, that negative 4 there, would get you negative a quarter. So you'd end up with negative 5/4. So be on the lookout for sine of 2y, cosine of 2y, e to the 2y, and then stick negatives in them. You're going to have to do little baby chain rules if that happens. Thankfully, all we got here was basically an extra -1. Now, mathematicians, unless you're told otherwise, do not like decimals. We like exact values. So that means that you might well have to play about with your answer so it's an exact value. If you plug in 1, you get 35 halves times 1. Take away 5e to the -1 minus, I'll plug in 0 here and plug in 0 here. Well, e to the -0 is just 0. Now that number is still 35 seconds. Isn't 5 to the 0, or I said 5 to the 0, isn't e, there we go, isn't, there we go, isn't -5e to the 0, the number -5, and so you're going to subtract -5, so you're going to add 5. Add 5 to this guy gets you, what, another 10, so basically 45 halves. Take away 5e to the -1, and there's your answer. Any questions about that one, apart from the little messy bit at the end? Okay. I'm not going to do this question, but I am going to start it. So I guess I'm not going to do it all the way at the end, but I am going to start it. What do you think you should do with this expression here, since you want to integrate it? And let me give you a clue. It's no good to leave it in that format. I need to do stuff to it to get it into a format that would allow me to integrate it.
I would expand that.
I would agree. And if you expand it, you end up with an x squared plus a 2xy plus a y squared. And then you can do the integration with x's, and then after you've done that, the integration with y's. Okay. Now, I would also do that if that was x plus y cubed. I don't think anybody would ever give you x plus y to the 4. That's just not fair, right? But you could do x plus y cubed. It'd be a little bit more work, but you could do it. Here's our next. By the way, I think that's something similar to 2. I'll just make one of my own up right now. Let's do x equals 1 to x equals 2, and y equals 1 to y equals 2. Okay, let's look at that double integral. So the guy I'm going to focus on is that guy, right? Well, with respect to y, 4x is essentially a constant, so you get 4xy. Y to the -2 is the power rule, so you add 1 to the power, and you divide by the new power, which makes it that guy. And xy is like 5y or 10y, in which case it's a power rule again. So you're going to add 1 to the power, and then divide by the new power. And we're going to evaluate that at 1 and at 2. Okay, if you plug 2 in for y, you get 4 times x times 2 plus 2 to the power of -1 plus x over 2 times 2 squared. That's the first part. Take away, if you plug in 1 here, you get 4x. If you plug in 1 here, 1 to the power of -1 is a bit weird, but it's 1. And if you plug in 1 here, you get x over 2 dx. So 4x times 2 gets me 8x. 2 to the -1, I'm calling it a half, it looks nicer. And 4 times that gets me 2x. So that's all those bits. Take away, well, what's that? 4x, add 1 and a half an x, so 9 halves x plus 1. Now, obviously, if you start doing enough of these questions, you probably aren't going to write every single line I'm doing. But, you know, I'm kind of doing it for completeness sake. So I have 10x add a half. Take away 9 over 2x add 1. See what that looks like. That's 20 halves. Take away 9 halves, so I'm going to get 11 halves. That's a half. Take away 1, I'm going to get negative a half. Now I'm going to do something that I do quite a lot in these questions when they're double integrals is, once you've done the first one, isn't the last piece just a calc 2 integral? And so what I'm doing is I'm just going to go dot, 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 dot. And that just means you could finish that off yourself because you know how to do, you know, calc 2, right? You know how to power roll it, plug in 2 and 1, get 17 thirds, whatever the answer might be. Are we okay at me just leaving a question at that point? And I'll, it means we have more time to do the fun stuff at the start. We're good?
Yep.
Yep, okay. So let's move back to some functions that have things that you haven't dealt with yet. So let's do a trig. And this guy is going to go -4 to 4. And it's going to be the y values. And then the x values are going to go from 0 to pi upon 2. And the function that I'm going to do is x cosine y minus y sine x. And there we go. So we're going to basically integrate some trig functions like sine and cosine. So that's the guy that goes first. So I'm going to do an integral from here to here. Yeah. Okay, with respect to x then, x cosine y, gets me 1/2 x squared cosine y. And if you do y sine x and you integrate it, integrating the sine is negative a cosine. The two negatives cancel out, and you're now left with plus y cosine x. And you're going to evaluate it from 0 to pi upon 2. If you plug in pi upon 2 here, you get 1/2 pi upon 2 squared cosine y plus y times the cosine of pi upon 2. Take away, if you plug in nothing here, it doesn't really matter what the rest is, you get nothing. And if you plug in nothing here, y times the cosine is 0. Right, y times the cosine is 0 is y times 1. Let's tidy it up just a little bit more. There's the -4. There's the 4. That guy gets me what? Pi over 8 cosine y's. What number is the cosine of pi over 2? what number is the cosine of pi
0.
over 2? It's 0. So technically, shouldn't have just pretended that was 0 and saved a bit of work. So 0, take away 0, take away 1.
Shouldn't it be take away a y, not a take away a 1? Because it was
Take
y.
away a 1y. You're right. Take away a 1y. Yes. And that guy, yeah, I might as well finish him. Integrate a cosine with respect to y, and you are going to get pi over 8 sine y. And this guy is going to get you, what, 1/2 y squared? And you're going to evaluate it from -4 to 4. And yes, the answer is going to look ugly, but ugly is still okay. It's going to be pi upon 8, the sine of 4, minus 1/2 times 4 squared. Take away pi upon 8, the sine of -4, minus 1/2 -4 squared. And so I'm going to get pi upon 8 sine of 4 radians. Take away 8. And I'm going to get pi upon 8, the sine of -4. And that's positive, so I'm going to get what? Take away 8. And if you take this guy, subtract this guy, and this guy, let's see what interesting things happen. If you take this guy first, take away this guy second, you then go -8, take away a -8, which is +8, and those two cancel out. So here is my answer. Maybe not the prettiest answer in the world. It looks like that. And I'm pretty sure WebAssign would accept that. Can anybody explain to me then? What I just did there, because this is equivalent to that. Can anybody see what I did to make that turn into this?
Sine's an even function, so you just pulled out the negative.
Right. Two negatives make a plus. Of course, since they're now the same thing, I can join them. So technically speaking, isn't that the best answer you could get? Although I'd be happy with that one, to be honest. I'd be happy with that one, but I prefer that one. Are we good? Yeah. Now, before we do the next one, I want to remind you of a couple of tricks of the trade that we haven't really employed yet. If you integrate e to the 5x or 4x or 24x, your answer will be e to the 5x with an extra 1/5. Are you all aware of that shortcut as one of the kind of rules of integration that you just take for granted? You could prove it by doing substitution, but typically we just assume that it's a known fact and you do it. You all recognize that guy? Now, in that same vein then, if you do the sine of 5x minus 1, integrating a sine will get you negative cosine 5x minus 1. But doesn't that 5x here generate a 1/5? So the answer is negative 1/5, the cosine of 5x minus 1. Still good? Now, you can do that with cosines, you can do that with tangents and all sorts of other stuff. Let's suppose we have to integrate something that looks like e to the 5xy. Right, that is going to happen, right? You're going to get things with x's and y's inside trig functions, inside e to the power functions. The integral of this guy with respect to x is e to the 5xy. What is going to be left outside? What's going to go here? When it was 5x, you got a fifth. What do you think is going to happen when it's 5xy?
1 over 5y.
Right. Now you see that's a little bit, I'm gonna say it's difficult, but I mean it's not common. You're not used to doing it yet. The more you do, the more you'll get used to doing it. And so if somebody gave you, for instance, the integral of xy, right, take away y cubed, but asked you to integrate it with respect to x, you have to know which bits do what things. That y cubed looks dangerously ugly, but it's actually not that bad. If you integrate a sine, you'll get negative a cosine of all this stuff. But as far as this extra little bit, right, the 1/5 or the 1 over 5y is concerned, it doesn't care that that's -1 or -40 or -10, right? It doesn't actually appear anywhere else. So that guy's pretty irrelevant. The only guy that's important is anything that's next to an x. Now, since this is xy, that will give us an extra 1 over y. Are you comfortable about the integral of this guy generates a 1 over y? Can you see what it's going? Right, so that's also going to be true when you do cosines and e to the powers as well. So keep that in mind for future reference. Let's return back to some of the more simpler ones. I won't say this is simpler, but interesting nonetheless. This is a version, question 6. And we're going to do x equals 1 to 4. I'm going to do y equals 1 to 8. And the function is the natural log of y over xy. And you're going to do dy first, and then you're going to do a dx next. So I'm going to set up the outside pieces for a minute. And now we're going to focus on that guy. So I'm interested in the integral from y equals 1 to 8, the natural log of y over xy. So I'm going to do this as a little bit of working at the side, and then I'll put the answer there. The power rule will not work. It's not a standard integral. This question is a u-sub. So you're going to have to do u-subs in some of these questions. And that means you've got to deal with the issue of what u-subs look like on top of all the other stuff that's going on, right? So there's a lot of balls in the air here. I want you to think of that as if it was, you know, like that, right? Imagine it was that guy, right? Just think of x as a constant. As long as it's treated like a constant, it won't cause you damage. Now, I need to know a u-sub. If I was doing this question here, right, the one with just numbers and y's in it, right, no x's. If I was doing this guy here, who would the u-sub be?
Natural log of u, or natural log of
Yeah.
y.
Natural log of y. And just because that's an x and not a 5 means nothing. It's still going to be the natural log of y. So if you're looking at a question and the x's are distracting you, pretend the x is 5 or something, right? And just say, well, okay, what would I do if it was this? Oh, okay, it's a u-sub and this would be my u-sub. Right, now back to this fella. It's been maybe a while since you've done this. You differentiate and you get 1 over y. You do a little thing called what I call the crossover, which is this guy. And then you divide both sides by y. Oops, I've lost my guy. Aye, aye, aye. If the brain would be dangerous. This guy is Y. Okay. This guy is Y. There we go. I found my Y. And I can do it there. Will you pretend I started from the scratch? Because my brain got into X mode and it just couldn't get out. So differentiate with respect to Y, and you get that. You essentially separate it into its differentials, and you will get Y du equals dy. And at this point, that's what I want. I want dy. So I can stop there. So the integral is going to look like that. The log of y is going to be u. There's going to be an xy here, and the dy is going to be y dy. And those cancel out, and now I have u over x du. So u there. That's basically just a power rule. So I'll add 1 to the power and divide by the new power. I'll then return the u to log y. So it's the log of y squared over dx. And at this point, I can then reintroduce the limits of integration. So when you do a u sub, especially when there's lots of variables, you do your u sub, convert it into a much nicer. If you don't like the way that's written, an equivalent way of looking at it would be that. Right? Does that help you see it a little bit better? Right? Integrate it, power rule, plug the log y back in instead of this guy. So it's essentially log y squared, and we're ready to go. So it's going to be the natural log of 8 squared over 2x, take away the natural log of 1 squared over 2x. Can't really do much with that, but I can do something with this. The natural log of 1 is 0, so that basically disappears. And I now have this guy. So we have the integral from x equals 1 to 4 of the natural log of 8 squared all over 2x. And if you wanted to do this next integral with respect to x, I would do a pretty major rearrangement. If you leave it as log 8 all squared over 2x and you try and think of what its integral is going to look like, it's going to get very messy. So all I've done is pull out everything and say it's a, it's a fractional amount of 1 over x. That makes the integral much easier. Because if you integrate 1 over x, you just essentially get log x, evaluated at 1 and evaluated at 4. So if you plug in 4, you get the natural log of 8 squared over 2 times the natural log of 4. Right, so that's the first one. And if you plug in 1, you get the log of 1, which is 0, which means all things 0, and we are finished. Not pretty, but correct. And I don't think there's any obvious style points that I could do with that. So I guess I'm finished. I kind of showed it myself there. There's lots of different letters floating about, but the minute you add in a U sub, isn't it even harder to keep track of, guys? Right, is that an X I'm doing? Is that a Y I'm doing? That kind of. Now, I'm going to show you a trick, a really cool trick. The question we just did a few moments ago. Which is that one. We can incorporate a very nice little rule. And the rule says if you're doing a double integral over a rectangular region, in other words, these are all numbers. We know that we can switch the order. I've talked about that. But you can do something else. You can separate them out. And the usual jargon I will say is that this integral is variable separable. What do I mean by that? I mean that you can do this. Separate it into two integrals. One integral that only uses the x's, the other integral only uses the y's. Now, can you see that in that last question we did, wouldn't this be much easier to do because they're essentially just calc 2 integrals, and you would still get the correct answer. Now, when are you allowed to do this? You're only allowed to do it when this function here can be rewritten as two things multiplied together, like an f of x times a g of x, or g of y, I should say, right? You wouldn't be able to do it if this was the case. Do you see in this case, you couldn't separate the x's and y's out? Agreed? But if it was that guy, I could separate that out. Couldn't I separate it as a 1 over x? And if you take this guy and you multiply it by this guy, don't you get the guy you started with? So you might want to look at some of the questions and say to yourself, are the variables separable? Because if they are, you'll be able to break it into two calc 2 integrals that you can do the usual way without having to worry about, you know, keeping all your letters in the right place. Here is a version, question 7. Is this integral separable? Is this integral here, is this expression, separable into so many things with x's times so many things with y's, and it's still be equal to that? Not obvious, and it's not, right? When things are separable, they're kind of obvious, right? We're not talking like you have to do some weird algebra and maybe it would be, maybe it won't. If it doesn't look like it, it's probably because it's not, which means this one becomes a typical double integral. Okay, let's see what that's going to look like. X over y is going to be integrated with respect to y. That's like 5 over y, right? 10 over y. If you integrate x over y, you will get x natural log of y. Are you cool with that? X over y gets you x natural log of y. What will y over x get you? If you integrate y over x with respect to y.
Y squared over 2x.
You'll agree? It's add 1 to the power, y squared, divide by the new power, add in an extra 2, there's your guy. You're going to evaluate it at y equals 1, y equals 4. So it's now going to be the integral from x equals 1 to x equals 16. So it's going to be x times the log of 4 plus what, 16 over 2, so that's basically 8 over x. Subtract, the log of 1 is 0, so I don't care about that. And this guy here is going to get you 1 over 2x dx. So you're going to be left with x equals 1 to x equals 16, x times log 4. I don't know if it's worth combining them. I have two minds. I'm not going to combine them. Instead, I'm going to write them like that. And then I'll combine them. So 8 over x, take away half over x is 7.5 over x. So that gets you 15 halves, 1 over x's. And at this point, I'm going to do my dot, dot, dot. Add 1 to the power, divide by new power for that one, and 15 over 2 log x for that one.
Can you
So again?
can you go over the evaluating the y from 4 to 1 real quick? The second.
Sure. Let's see. You plug in 4, you get x log 4. 4 squared is 16. 16 over 2 gets me the 8, so 8 over x. Take away, if you plug 1 in, the log of 1 is 0, so x times 0 is 0, so I won't write anything. And if you plug in 1 here, you get 1 squared over 2x, you get that guy. Now, these two guys are eventually going to combine, but I kind of had to think about how I'm going to do it. 8 over x is fine. Actually, you can think of it as 8 times 1 over x. And this guy here is like a half times 1 over x. So that when you combine these, you get 7.5 1 over x's, which is where that came from.
Yeah, thanks. Arithmetic was just mixing up in my head.
But I mean, it's kind of messy. I could probably have got away with not tidying those up, because once I do the next integral, it will have sorted itself out anyway. Are we good with that one now? Great. Okay. Oh yeah, we're going to have to. Right, let's move up the food chain. The integral from 0 to 6. The integral from 0 to pi upon 2. The variable is going to be from 0 to 6 is t. And from this guy, squiggle equals 0 to squiggle equals pi upon 2. And this guy is going to be a t squared sine cubed squiggle d squiggle dt. Or if you prefer not to use the word squiggle, you can call it phi. Except some of you Americans want to call it something else, so that's why I'm calling it a squiggle. Now, that is an ugly looking double integral. And if I see an ugly looking double integral, I'm always looking for things that will make my life easier. Is this variable separable?
Yes.
And because of that, it becomes the integral from t equals 0 to t equals 6 of t squared dt times the integral from squiggle equals 0 to pi upon 2 of sine cubed squiggle d squiggle. Right, I'm not even going to talk about that one. Isn't that a third t cubed and you get a number, right? That's baby stuff. This one I am going to talk about. Let's do this one on his own sum. Because you are going to be doing a lot of integrating, right? And so we gotta, get back into that Calc 2 mode. This is not a power rule. So don't say, oh, add 1 to the power and, get a quarter, right? So it's not a quarter sine to the 4th squiggle. That is not how you do this guy. And trig, in fact, there's a whole section devoted to it in Calc 2, where we deal with how do you integrate things like this. This particular one is actually a U sub. who knows, 6 months ago, whenever you did this Calc 2 stuff. Can you tell me what is the only U sub that is going to work with this integral? Now, looking at puzzled looks here, I'll
Sine
give you a
cube.
clue. Let me give you a clue. I'm not going to call that guy sine cubed anymore. I'm going to split that guy. And I'm not going to leave it as a sine squared anymore. Okay, let me ask you the question again. What is the U sub now? What would you use on this expression as your U sub?
Cosine?
Yeah, cosine. Now, did you notice that it wasn't even vaguely obvious that the cosine was the right one when it was written like that? In fact, if I'd left it like that, I would be in real trouble trying to solve the problem. You had to do a bit of algebra. And so the trig integrals are the ones where there's always little twists and turns, and they've never, it seems almost like no two of them are the same, right? So you've got a lot of variation in them. Well, now I've got the correct U sub, I'll differentiate. And if you differentiate a cosine, you get a negative sign. And then I'll do the crossover. And then I'll divide both sides by a negative sign to isolate him. So our integral is now going to be 1 take away u squared sine of phi times 1 over negative sine of phi du, which means it now becomes negative 1 minus u squared du. And we'll keep going. I would probably distribute the negative to get that guy. Now I can use the power rule. Negative 1u, add 1 to the power, divide by the new power. Convert back into cosines. And then put in the limits of integration, which are from 0 to pi upon 2. And then at this point, you just plug in it and, actually, quite interesting. Let's take that. You get negative the cosine of pi upon 2 plus 1/3 cosine cubed of pi upon 2. Take away negative cosine of 0 plus 1/3 the cosine cubed of 0. The cosine of pi upon 2 is actually 0. So these two pieces are 0. The cosine of 0 is 1. So that's negative 1. So we got negative 1. And that is plus 1/3. So you're going to have 0, take away negative 2/3. Oh, the answer ends up being 2/3. So we're now coming into that place where you're going to have to find integrals for things that aren't just power rules or pretty simple standard integrals. We're entering that place where U subs are going to be required, right? Maybe even an integration by parts now and again. Okay, here's a version of question 9. and it's 4xy times the square root of x squared plus y squared dy dx. Okay, we are really entering into quite interesting puzzles. I need to integrate this expression with respect to y. The x's are really just numbers, right? They're like 4, right? So that's like, what, 16y, and that's, 16 plus y squared. And so we have to figure out, and I'm going to do that on a separate piece of paper right now, how to integrate this ugly guy. When I go through my toolbox for how to integrate things, it's quite a limited selection. Power rule, right? Use that a lot. Standard integrals, right? I know what e to the x is. I know what sine of y is, things like that. I know 1 over y is a log. I can do those. The third and probably most useful is u-subs. Now, you might now and again, like 1 or 2 questions kind of now and again, come up with an integration by parts question. But the chances are that u-subs are going to be the guy. So when you look at an integral and you know it's not a power rule, and you can tell looking at it it's not a standard integral, then you should probably be thinking u-subs. And don't see x's anymore. See 42s, right? Just see numbers there. So based on what I have said here, what would be the u-sub for something that looked like that?
I would just substitute y.
Well, if you did u equals y, the question would basically just end up looking as it did at the start. So, little rule for you. There is no useful use of u equals y as a substitution, right? So, you're never going to do that and get anything benefits. So we have to look at this as, well, if you need numbers, if I went and said to you, 42y, the square root of 9 plus y squared dy. If I said to you, what would the u-sub be this time? Does that help? What would you do as your u-sub in this question with all the numbers now?
It's gonna be everything inside the square root.
Square root, yeah. And so since this is the same situation, there's your u-sub. So if you get stuck because the x's are just, playing with your brain and they're stopping you focusing, turn the x's into any numbers you like. Doesn't even need to be the same number, right? Just turn it into 4s and 3s and 2s and whatever you want and say, okay, what would I do here? And now the u-sub is everything in the square root. So that makes this the u-sub. If you differentiate it with respect to y, got to make sure we use the right variable, x squared gets you nothing. All you get is 2y. If you do the crossover so that you're isolating the differentials, and if you divide both sides by 2y, you isolate the 2y. So forget that again as a distraction. We're going to have the integral of 4xy times the square root of u, and instead of dy, we're going to have 1 over 2y dy. And the y's are going to cancel, and the 2 is going to partially cancel. So I'm going to have 2x, the square root of u, that's a u here, the square root of u du. Now, I don't care what x is, because x is a constant. Basically, I'm trying to integrate with respect to u to the half. So I will add 1 to the power. And then divide by 3/2 is the same as multiplying by 2/3, so I'll get that. I will then turn the u back into x squared plus y squared. I will then do style points, which is make it look like the original. So 3/2 is a square root of that guy cubed. So our integral of this guy here is going to be 4/3 x, the square root of x squared plus y squared cubed, evaluated at y equals 0 and at y equals 1. So that's going to be the integral from x equals 0 to x equals 1. And let's see, if you plug in 1 here, you get 4/3 the square root of x squared plus 1 cubed. Take away, if you plug in 0 here, you get 4/3 x, the square root of x cubed dx. So we're going to get the integral from 0 to 1, 4/3 x, the square root of this guy cubed. X cubed is really x square root of x, so that's what, 3/2, that's one more. So take away 4/3 x to the 1.5, x to the 2.5, x to the 5/2. All of that gets you 5/2. Now, we've done half the question. We have integrated the first part with respect to y. Now we have to integrate this guy. This guy is a power rule. What would you do to integrate this ugly thing?
Probably rewrite it in a similar fashion as you did the x to the 5/2.
And
And
then
then
when you
do-
do a u sub, Jesse, put more
Yeah.
on that. And the u sub would be x squared plus 1. Right. Take you a while, but you'd get it. Okay, so we've left the nice place, right? And we're into the deep waters here, right? We are not getting any freebies anymore. Here is a version of question 11 then. And we're introducing some new notation. So I'm doing, really all I'm doing here is an exact copy of what WebAssign is doing. Right, this double integral needs to be set up with dx's and dy's and with limits of integration. And I think it's pretty obvious that the x's go from 0 to 4 and the y's go from 0 to pi upon 4. Agreed? So I'm going to set it up as from x equals 0 to x equals 4, and from y equals 0 to y equals pi upon 4, x secant squared y, and dA is really just a placeholder. And it's technically an areal differential, dA, but what it really is really just dx dy, or dy dx, you can pick, right? Just a placeholder for those two guys. Since I've decided to do the y's first, followed by the x's, when I have to write my dA that way, right? Are you comfortable about how this notation turns into this double integral? Are we good with that? Oh, somebody in chat. Wish I'd paid attention. Right, so you're talking about exams. You are expected to know all standard integrals. There's about 12 of them. And yes, you could get this question in an exam. So if you're interested in the standard integrals, the ones I'm talking about, I'll put together a sheet with them on it. But just think of e to the x, secant squared x, you know, sine x, cosine x, all the standard ones. And if it was some weird integral that you've never seen in your life before, I'd either just not give you it, or I would tell you what the integral of it was, which would be a pointless exercise. Now, let's look at this guy. We've turned it into what is the way that it kind of needs to be written so we understand what we're being asked to do. Is there any shortcut you could do here?
Separate it.
Why don't we? If you can separate one of these, do it. Right? It's just going to make life easier. I can't think of any situation where it would make it worse. Now, this guy here is pretty easy to do, so only for completeness sake, I'll do the power rule on it. And if you plug in 4, you get half of 16, so you get 8. So this one is one of the, as I think I said earlier, it's about a dozen standard integrals. Does anybody know what the integral of secant squared y is?
Tangent.
That's a tangent, right? So you're going to be doing the tangent of y from y equals 0 to y equals pi upon 4. And to save some room here, I'm doing this in my head. The tangent of pi upon 4 is 1. And if you look up your unit circle or whatever, you'll get that. And the tangent of 0 is still 0. So basically that gets you 1, so the whole answer is 8. So the tangent of pi upon 4 is 1. So 8 times 1 is 8. And I just did a quick look, and it is correct. Okay, I want to integrate this guy. How's it going to work? I mean, it's not a lot going on here, so whatever it is, it can't be too much. Any ideas? Okay. Imagine
You can,
that
so it's going to be your kind of reverse chain rule, but since the x is like a constant, it's going to gain a y when you do the,
well, switch it the way around. It's x is first, y second.
oh yeah, yeah.
But it's the same idea, right? This guy is equivalent to that guy, right? I'm just turning the y into a number to make it easy, right? So what were you saying again, Jason?
So you could do a u sub, but it's kind of,
There's a shortcut version
yeah,
of
it's
it,
a little,
right?
little short. You just 1/2 plus 1 is 3/2, so you're dividing by 3/2, and then also dividing by, was it that?
No, no more. That's all. Yeah. Think of it as that. Add 1 to the power, divide by new power. Now, if that was 4x or 2x or 7x, then you'd have times a 7. But since it's a single x here, isn't it technically times 1 over 1, which doesn't matter. So there's your guy. Now, you doing this fella. Think of him as x plus y to the half, like this. Add 1 to the power, divide by the new power, times 1. Right, 1x. I don't care what that is, right? X plus 50 or x plus 40, don't matter, right? It's just 1x plus a number, so times 1. And so that becomes m. So this fella here, this guy here, he comes 2/3 the square root of x plus y cubed, evaluated from x equals 0 to x equals 1. So if you plug in x equals 1, let's see what we get. We get 2/3 the square root of 1 plus y cubed. And if you plug in 0, you get 2/3 the square root of y cubed. So plug x equals 1, plug x equals 0. Now I'll do a little tidying up before we progress here. That guy I'm going to call 3/2. And this guy I'm also going to call 3/2. And do you see that these two guys are basically just power rules? And this one you could, if you wanted to, do as a u sub, but it's nice enough you could do the shortcut. Make sense? Okay, let's see where we're off to next. Oh, won't do all of the next one, but it's a good one to bite our teeth on. We're going to do a, well, I'm cutting out the middle, man. They actually do it with the limit R and the DA thing, but I'm going to just write down what that would eventually be just to save some time. So we're going to do a y equals 1 to y equals 2, and we're going to do an x equals 0 to x equals 2. And the function that we're meant to do it with is 3xy squared over x squared plus 1, a dx and a dy. And I'm just checking my x is 0 to 1 actually. And my y's are negative 2 to 2. So I've got, right, 0 to 1, negative 2 to 2. I don't know how to phrase this without giving too much help. So let me not phrase it at all, except to say, what do you do next?
You know what we have to do.
Oh, so we're both doing that. You're right. We do know what to do. It is going to be variable separable. Agreed? Now, when you make it variable separable, don't you make your life 10 times easier than it would be if you couldn't separate it. That one is a power rule. What would the u sub be to make this one work?
X squared plus 1.
Right, and off you go and do your thing. So I guess in a way, shouldn't you always be looking or be on the lookout for variable separable, right? So this is 14, or a version of it. Again, I'm setting it up so we don't have an extra line where I write down the question and say it means that. This question, I think, is kind of cool and also a pain in the butt. The kind of cool part is, would you agree it's variable separable? Right? Now, the way it's going to separate is that this guy becomes a 1 over, and the other guy is what you'd expect it to be. The pain in the butt part is the two pieces, right, which are Calc 2 integrals now, right? They're just normal Calc 2 integrals, are not the standard, oh, it's a power rule or it's a sine theta, right? Each one of them is a pain in the butt in a different way. Let's start with this one. Do you recognize this as one of the 12 standard integrals? Because it is. What is this integral?
Sine inverse t.
You nailed it. So,
Could we see
inverse
that
sine
with
t. Say again?
How would that look like if it was a double variable? So it was like the square root of 1 minus zt or z squared t squared. Would that just be? We've had questions.
That one, Kel, would actually be a u sub, and then the u sub would become an inverse sine. So right off the top of my head, if that had said, I don't know, z squared or something t squared, right? If there was an extra variable here, this would be the inverse sine of zt, and you would also get a 1 over z outside, and you wouldn't really be able to see that until you did maybe a u sub on it, and the u sub would have been zt, right? So if this is 1 minus z squared t squared, you do that. That is a horrible, I mean, it's doable, I guess, but it would be horrible. I think this is bad enough. Now, how about tan theta? It is not a standard integral, although you might know the answer to it, and that'd be really cool if you did. And so let's think of it more as, what method should I use, or how should I get the answer to this? Any thoughts on a different way to write tan theta that would allow me to be able to integrate it? Any thoughts? Tan theta. Oh, somebody in chat. Let's sign up. Okay. Someone wrote a comment. Right. Last chance. Tan theta. That's the end of my clues. It's a fraction.
Sine over cosine, then do a u sub.
Yeah, exactly. Sometimes don't you just need that little shove, and then you go, oh yeah, got it. Sine over cosine u sub. So sine over cosine u sub, get your answer. I won't do that part. Let's do a little bit more of this fella, because we don't really deal with inverse trig functions that often. Right, that would be the calculation, right? There'd be a 0 here. The inverse sine of 0 is what angle has a sine of 0, which is 0. The inverse sine of root 2 upon 2, right? Think of the inverse sine as being an angle, right? Pi upon 2 of that. The inverse sine of root 2 over 2 is what angle has a sine of root 2 upon 2, and the answer to that would be pi upon 4. So this piece of the puzzle would be pi upon 4, and this piece of the puzzle would be whatever you got. We cool on that? Right, suppose they put cotangent here, because I guess they could, right? Wouldn't you call it cosine over sine and do a different u sub? Right. So tans and cotangents are treated in a very similar way. I'm not quite sure what's happening in 15. So again, we'll set it up the way that they, oh no, they won't. I'm going to have to do the whole setup part. You're being asked to find that double integral, and R is given using this rather unusual notation. Okay, so we're going to do a double integral over some region R, and this is the region R. Now I need to know the limits of integration of X and the limits of integration of Y. The convention is that this guy is the X's and that this guy is the Y's. That's the convention, right? So what I'm going to be doing is X equals 0 to X equals pi upon 6. And I'm going to do Y equals 0 to pi upon 3. And I'm going to do 5x, the sine of X add Y. And the dA is a placeholder in this particular combination. It's for dy by dx. And this one, I believe, is the first one where we have to do integration by parts. So I want you to imagine that you were being asked to integrate that. Right, so all I'm doing here, oops. It's interesting. I take it back. I don't need integration by parts yet. I'm pretty sure I'll need it next. But since I decided to do the Y's before the X's, I have to stick to my rules. Well, if you take this expression, right, and you integrate it with respect to Y. So 5x, the sine of X add Y, is going to be integrated with respect to Y. You do not get that much. You still get 5x. If you integrate a sine, you get a negative cosine. Technically times 1. So who cares? 1 doesn't make a difference. You're going to do Y equals 0 to Y equals pi over 3. So it's going to be the integral from 0 to pi over 6. And it's going to be negative 5, the cosine of x plus pi upon 3. Take away negative 5x, the cosine of x add 0 is just x dx. So we're now going to be integrating the 0 to pi upon 6, negative 5x, the cosine of this guy, plus 5 over x, the cosine of this guy. Okay, we are going to be doing integration by parts. If I asked you to integrate just this piece, that is a classic integration by parts guy, isn't it? Remember, integration by parts is essentially deals with integrating two things multiplied together. Now, there are two totally different techniques used to integrate this. One is the f of x, g of x one, which is one I teach, and the other is the UDV method. So some of you have done this as a UDV method. Some of you will do this as an f of x, g of x method. If you do it by the f of x, g of x method, you will make that f of x and you'll make that g of x. And the formula is f of x, capital G of x, take away the integral of f dashed x capital G of x dx, where capital G of x is the integral of g, and obviously f dashed is its derivative. So we'd get 5x. If you integrate a cosine, you get a sine. Take away the integral. If you differentiate this guy, you get 5. If you integrate this guy, you get sine x. And now you get 5x sine x. And integrating 5 sines gets you negative 5 cosines. 2 negatives give you a plus. And you've got that guy. And then you then do it from 0 to pi upon 6. Do you remember that method? Integration by parts. It's not as common as the U sub, but now and again they happen. Here's one of the now and agains. If you do the UDV method, you will get exactly the same answer. It's not like one method gives you, a different answer than the other. Teresa, put you in the spot. Do you remember doing integration by parts?
Yes.
Do you use the FG method or the UDV method?
Well, I first did it with the UDV method. I
Right.
think I like this way better.
Okay. So you're kind of lucky because you're ambidextrous now. So you can jump from one method to the other depending on your professor, right? And you're comfortable with both. Right. For the rest of you, you have done integration by parts. If you do not like this method, that's totally fine. I understand that. Just do what you would do using the formula I'm calling the UDV method. You will get the exact same answer. Now, this has got a bit of work to do, but I'm not going to do any more. The other piece was this one, and it was negative 5x, the cosine of x plus pi upon 3 dx. And that is also an integration by parts. This bit is the f, and this bit is a g. So we get f of x, capital G of x, take away the integral of f dashed x, capital G of x dx. Leave that guy alone. If you integrate the cosine of x plus pi upon 3, all you get is the sine of x plus pi upon 3. Technically times 1 because of 1x. Take away. You differentiate this guy, you get negative 5. You integrate this guy, you get sine of x plus pi upon 3. And so you get negative 5x, this fella. Okay, if you integrate, oh God, there's a lot of negatives floating about here, isn't there? If you integrate sine of pi, you get negative cosine, but that makes it plus, but that makes it back to being negative. So you get negative 5 cosine of x add pi upon 3. You can then evaluate that at the pi upon 6 and at the 0, and plug and chug, and off you go. Are we okay with that one? Integration by parts, can't avoid it. That's what you have to do. Here is a question that looks almost identical. Let's suppose you ended up having to integrate that. Right, that could happen. That's not integration by parts. What method is that one?
U sub.
And isn't the u sub x squared? Do you see the difference one little thing can do to the method you're going to use? Right, so power rule, right? Use that quite a bit, especially at the start of today. Standard integrals, right? I know what the square root of 1 over 1 minus d squared is, right? 12 of those guys. U subs, use them a lot. Integration by parts, at least so far, we've only used it 1. But guess what? We're already at question 15, and it's only happened once, right? So it's probably going to be the least used method. Any questions before we move on to our next guy? Okay, and here is the next one. This is a version of 16. You're going to do x equals 0 to x equals 2. And you are going to do y equals 0 to y equals 5. And the thing you're going to integrate is that guy. Okay. So x equals 0 to x equals 2. Put a dx here. Let's focus on this fella. And I'm going to do him at the side. Okay, since y is the variable, this guy is the same as doing y e to the minus 3y dy. Agreed? Just replace x by a number, right? So the way I would solve this is going to be the same way I'm going to solve that. Do you see an integration by parts? You see it? Integration by parts. So I'm going to call this piece F, and I'm going to call this piece G. And so it's going to be, well, I don't know why that's so big. FG, take away the integral of F dashed G, right? In this case, dy. That guy is y, and this guy is going to get integrated. Now, if I asked you to integrate this fella, the answer would be that guy times negative a third. Great. So when you're being asked to integrate this guy, you're going to get e to the negative xy times a negative 1 over x. Are you happy about where that weird negative 1 over x is coming from? Right, it's coming from the minus x next to the y. Right, essentially you divide by negative x. Take away. The derivative of this guy is 1, and this guy you already know is equal to this fella. Just tidy this up a little bit. A negative of a negative is essentially a positive, and now I have that integral to do. That 1 over x is totally irrelevant. It's like 1/2. It's just a number. So we have this fella. Now, if you integrate this guy, you get 1 over x e to the negative xy times another minus 1 over x fella. So you have that guy minus 1 over x, that guy. And now I can plug in the y equals 0 to y equals 5 part. Now, if you plug in 5 here, you get negative 5 over x e to the negative 5x. Take away 1 over x squared e to the negative 5x. And if you plug in 0 here, you get negative y e to the 0, negative 1 over x squared e to the 0. And I just realized something. I made that question 10 times harder than it needs to be. And I didn't realize it until I got to here. Because when I get to here, I'm going to say, oh God, would you look at how ugly that integral is? And I'm now going to return back to the original question. Remember this guy? And I am going to do the following. And I think I even mentioned it at the start of today. Aren't you allowed to switch order? Right? Now, by switching this order, let's see if my question, instead of being ugly and almost impossible to do, turns into something much cleaner and nicer. If you integrate y e to the negative xy, it's a bit like 5e to the negative 5x, right? Just think of y as a number. You will get y e to the negative xy times, now since you're doing it with respect to x, a negative 1 over y, which is really cool because all you end up with is that guy. Would you agree that that way around was just so much cleaner? So the integral from y to 0 to 5, let's see, if you plug in 2, you get negative e to the negative 2x, take away negative e to the 0. And so you've got, I get an x or a y here, y, there we go. Then I'd get from y equals 0 to 5, negative e to the negative 2y, essentially plus 1. And that guy is dead easy to integrate. So I guess the moral of that story is, 1, shouldn't you always look for variables separable? That I've been pretty good at today. 2, sometimes isn't it better to switch the order? To do the x's before the y's or do the y's before x's? So have a quick look to see if that makes your life easy. That was so darn simple. How did I know that I got it wrong? Right, integration by parts. Can you see this guy here? Do you really want to integrate any one of these two with respect to x? Because that's what's going to happen next. The minute I saw that, I started worrying. And then I said, oh, darn it, why didn't I just switch order? And, you know, that's going to happen. Hopefully you will find, if that happens, you'll find it out a lot quicker than I did, right? You wouldn't have done all that extra work. Oh. Okay, next one I have to show you, because it's visual. I'm not sure if this is a great picture. I think mine was just as bad, so I shouldn't really criticize them. But here you have your function. Here is your rectangle. And you're being asked to set up the integral that would calculate this, right? So if you look at the bottom, can you see x goes from 1 to 2? And can you see that the y goes from 1 to 3? Are you comfortable about that? Now, what's the function? The function is this guy here. So you pretty much are going to type in 4 in brackets x squared plus y squared. And evidently I've got more brackets than I need there. Now, if you want to integrate that guy, it's really not a horrible integral at all. Then you just have to be aware of limits of integration and how you're going to break it apart. So it's going to be the integral from 1 to 2, which is the y's. Was it y's or the x's? X's. So it's from x equals 1 to x equals 2. Let's try that again. From x equals 1 to x equals 2, and from y equals 1 to y equals 3. And 4 lots of x squared plus y squared dy dx. I'm not going to make this complicated because it doesn't need to be. it does help if you distribute the 4. Yeah, would you agree that's a pretty straightforward integral? No frills. You got your answer. Any questions about that one? Okay. Let's look at 18. Find the volume of a solid that lies under the plane 4x plus 6y take away 2z almost forgot it, plus 15 equals 0. And it's to be above the rectangle. And the equation, the rectangle is given as x is between -1 and 4. And y is between -1 and 1. So I guess the only thing that's kind of a little bit weird is that the equation that we're given is not written in the way it needs to be written, which is z equals, right? Z should be a function of xy. So I'm going to do from x equals -1 to x equals 4. I'm going to do y equals -1 to 1. And the function that we're going to deal with is this guy rearranged so it becomes z equals. So let's do that over here. So yeah, it's a plus 15 equals 0. Well, if you subtract 4x, 6y, and 15 from both sides, you get that. If you divide everybody by -2, you get that. So this fella is essentially your f of xy. So 2x plus 3y, add 15 over 2 dy dx. Are you comfortable that that would be a pretty straightforward integral, right? Integrate with respect to y, integrate with respect to y, integrate with respect to y, plug in these two numbers, get an answer, and then whatever's left, integrate with x. Is it okay for me to leave that at that point and just do a ... Or do you want to see more? Thumbs up? Okay. We're getting close to the end. So in the next question, they ask you to find the volume. So it's kind of like 18. In fact, let me just keep 18 where it is. And they tell you that z is equal to y squared take away x squared plus 3. And they tell you r in terms of that, you know, the square brackety thing. So the volume is going to be the double integral from x equals -1 to 1 and y going from 1 to 2, because the convention is when they write it like this, these are the x's, these are the y's. The function that we're going to do is actually given to us, dy dx. And actually, again, would you agree that's a pretty simple integral, right? Integrate with respect to y, plug in the numbers, integrate with respect to x. Kyle, you have a question? No? Okay.
No.
Thought you, yeah, no? Okay. My mistake. So when they talk about find the volume of something above or below the xy axis, doesn't it just boil down to a double integral? This guy here is the z equals bit, and these are the limits of integration. I think they've got 2 more of these and we'll be, is it? No, it's 3 more of these. So here goes. The next one is that guy, and it's -1 to 1, and negative 2 to 2. Right. So I'm going to do the integral from negative 1 to 1. Y is going to be negative 2 to 2. Going to have a function here, dy dx. I guess the only thing I need to do is that if you don't tell me the thing in terms of z equals, don't I just rearrange it so that it is z equals? So in this case here, if you rearrange it, z is 1, take away that, and now you can put in the value of z here. And it's kind of like the other two questions, right? That would be what? Add a y, and that would be a power rule, and that would be 1y. And then plug in the numbers and get your answer. So our last question is going to be quite a long one. And it's a version of question 23. And we're being given a function, f of xy, and it's 2 e to the y, the square root of x plus e to the y. We're told, and I'm just telling you what they are, the x's are between 0 and 4, and the y's are between 0 and 1. They actually did it with the boxes. And instead of asking us the usual question that they ask you, right, is to find the double integral, right? So it's going to be from x equals 0 to x equals 4, and from y equals 0 to y equals 1 of this function, which is the normal kind of thing that you need to do. You're being asked to find the average of a function. So what is the formula for finding the average of a function? Well, it's this integral, 1 over the area of the region R. Now, this is the region R. If you draw a little rectangle guy, can you see it's 0 to 4 and 0 to 1? And would you agree that the area of R is 4? Are we good with that? Right. So all we're going to do is find 1/4 of the integral from x equals 0 to x equals 4, y equals 0 to y equals 1 of this function. We cool? So the average value of a function is 1 over the area of the rectangular region, which in this case is 4, and the usual double integral of the function. And you can think of that, imagine that the function f of xy was the temperature at any given point on the surface Z. So what we're essentially finding is the average temperature on a weird bent plate. I'm going to do another little sneaky thing. I haven't done this. Probably could have done it earlier. Do you know if this is a number, not a constant, but a real number, 10, 4, 2, you can bring it outside. And it's really up to you. Did it make the integral easier or not? I don't think there's a lot of difference between doing this one and that one, but maybe you do. I think it might be more useful if this was really messy, you know, like 14/17 or something. Couldn't you just pull it out of the integral and then you don't need to worry about it? So that's now going to be a half. We're going to do the integral from x equals 0 to x equals 4. And we're going to do this guy.
Couldn't we
I'm gonna do-
switch the order of the integrals this time?
Did I accidentally? Are you saying could we switch them?
Yes.
You could. I think this time, if you switch the order, in other words, done the x's first and the y's second, I think the integral ends up being really horrible. You'd have to check it out, but I think this way around is actually going to be, it's going to be nicer. But I could be wrong. Check it. Do it the other way. If it's doable, it'll work. But I've got a feeling it's probably ugly. So let's do this guy at the side. Yeah, let's do that guy. Now, superficially, I don't want to integrate this with respect to y either, right? It looks really horrible, but it's actually not as bad as it seems. Just a little cosmetic. This is like e to the y, 4 plus e to the y to the power a half. Do you see a u sub?
X plus e to the y.
Yeah. And if you differentiate this with respect to y, you just get e to the y. And if you do the crossover, you get that guy. And then if you divide both sides by e to the y, you isolate the dy. So I'm now going to have the integral of e to the y, u to the half, times 1 over e to the y du. And it now becomes, oh, would you look at that? Is that not pretty? I wonder if you went the other way, it would be as nice. Right? I don't think so, agreed. So add 1 to the power, divide by the new power, return back to your original, and now evaluate it at 0 and at 1. Right, if you plug in y equals 1, let's see what you get. X plus e to 3 halves. And if you plug in 0, you get 2/3 x to the 3 halves, right? So that's what we get. So this bit here is him. So switch places. Two-thirds x plus e to the 3 halves. Take away 2/3 x to the 3 halves, right? So we've done half the stuff. I'm now going to integrate this with respect to x. That guy there looks really bad, but he's actually not. So here goes. Add 1 to the power. Divide by the new power, which means multiply by 2/5, and so you get 4/15 here. Since this is x plus e, technically, don't you just multiply by 1? It's a bit like sine x plus 1, e to the x plus 1, right? You don't really get much. That's it. This guy, add 1 to the power, divide by the new power, and now we can evaluate it at 0 and at 4. So the average value of the function is, let's see what we get. 4/15, 4 plus e to the 5 halves, take away 4/15 times 4 to the power of 5 halves. Oh, God in himmel. Put in 0 here, and you get 4/15 e to the 5 halves. Oh, take away nothing. Okay, so we have 1/2. I got 4/15 that guy, which really isn't going to come out as anything nice. That guy there is not bad, because what you get is 16, you get 32, and 4 32s is 128. Is 128/15, but check it. And that guy there's not much. And allegedly, this answer is about 6.654. I'll trust WebAssign for that. Are we cool with this guy? Right. Oh, pretty good timing. Almost exactly on the spot. 7 o'clock. Right. Bye-bye. I'm going to hang about for any questions that you might have. Maybe there's something I did today that you never got a chance to ask about. Otherwise, bye-bye, and I'll see you on Monday. To remind you, homework, test, and basically that's it, is due now on Tuesday. So you have 2 more days. Right, we've extended the deadline for online test 3 and homework assignment 3.